Hey guys, I'm going to do problem set number 4. I'm not going to go over the answers, I'm more going to go over concepts and maybe a difficult example for a practice problem. Okay, again, this is for my study, not necessarily yours, but if you find these helpful, that's great. Okay, first thing we went over is the natural abundance equation, and so how to use this. So I drew boxes to maybe you can hopefully see, but my handwriting's also bad, so maybe it doesn't help. Natural abundance of an element and or compound is equal, nope, it's just element of an element, is equal to the percent times the isotope. So the isotope, so the percent abundance, this is, an isotope is like, for example, 50% abundance. So 50% of all elements of this element is this certain isotope. Maybe that doesn't make sense. But this percent times that isotope plus another percent times another isotope. And again, this is the, of all the elements that exist, this percent is how many of those elements are this isotope. That's a better way of saying it. And you keep doing that for how many isotopes you have. So remember that the percents added together are going to equal 1. So A% plus B% is equal to 1. So if you're looking for a percent, or say you have two unknowns, you have an isotope that you don't know what the mass is, or the AMU is, and a percent that you don't know how abundant it is, that would be two unknowns, and so this is your second equation to figure out between the two equations what that unknown is. And then you'd be able to find out not only how much the isotope is in AMU or grams, but you'd also be able to find out how abundant that isotope is. Okay, good. Spent too long there. Just remember sig fig check on this. When you multiply by percents, you're going to get the same amount of sig figs between these two, or the one with the least amount of sig figs between these two. So say you, and so keep track of that. But then you're going to add. So for example, say I have 3, I'm going to use SF, sig figs there, and 4 sig figs there in that isotope, and I'm going to put this to that isotope. And then 2 SF in that percent, and 3 SF in that percent, okay? So obviously this one, because 2 is the least amount of sig figs, then the percent times this isotope it's going to end up with 2 sig figs, and then this one's going to, in this multiplication, it's going to end up with 3 sig figs. Say these 2 sig figs only bring me to the 10th place. So 1, 1, 1. So it only brings me to there, the 10th place. That means that when I add them together, that in my significant figures, that I'm only going to have added up to the 10th place. Okay, so watch it on there. It's a combination, so you want to use both of the multiplication rule and the addition subtraction rule. One thing that wasn't really talked about a whole lot in class, but was talked on the problem set, was the charge of ions. And so this, just over simply, this is my poorly drawn periodic table, but I'm just going to say that you got to think about it as, for an ion to come together with another ion, it has to have opposite charges for one, so a negative and a positive charge. And you want to think about how hard is it for that ion to give up an electron and or gain an electron. So I'm going to split this table in half, or really the more splits like right there. Everything on this side of the table, it's easier to gain an electron, and so all the ions are going to be negative charges. By this row has no charge, but then this is a -1 charge, -2, -3, and so on and so forth. I think it goes to 4 and then switches. So that's my poorly drawn table at fine work. Then on this side, it's going to be the opposite. It's easier to lose an electron over here because it's, and so it has a positive charge. So if it was an ion, it has a positive charge. So it would be a 1 plus, 2 plus, 3 plus, so on and so forth. Okay, hopefully that makes sense, but like read it back, forward and backwards and say this side it's easier to gain an electron, so it has a negative charge, and then this side it's easier to lose an electron, so it has a positive charge. Okay, a lot of dimensional analysis in this problem set. Just remember, it's easiest to start with what you have and then what you want on the far end. And then just start with what you know. You say, okay, how do I get, like, what from what I want do I get? And so maybe you can come in 1 here. Or I have this and I know that 1 mole goes into this of 1 of what I have, or something like that. And then start there. Watch your sig figs though. Molar mass was also talked a lot about in this. Just know there's not a huge conversion of dimensional analysis that you have to do in molar mass because of Avogadro's number and how he calculated it. The same number in AMU, so for example 15.999 AMU for oxygen, this converted to just a molar mass in grams is going to be 15.999 grams. And that was done on purpose. That was done on purpose by Avogadro and that's why the mole is the number that it is, because that's what the conversion is from AMU. And so when you're looking at molar mass and you're adding them together, or you're multiplying to find how much a compound weighs, look at just the AMU and then put on grams, and then you can find 1 mole of that thing. Okay, but in a compound, how you tell how many moles of a specific atom you have? That's simple. If I had H2O, just look at this number 2. And so if I say I have a mole of H2O, how many moles of hydrogen 2 do I have? Or more like, how many moles of hydrogen do I have? And that's easy. That's just 2 times 2 moles. 2 moles because it's just doubled that of how many moles you have of this. So don't overcomplicate that one either. Most of my homework, I overcomplicated that one. Okay. Dimensional analysis on atoms. Just remember, start with what you have and then end with what you want. Try and cancel as much as you can out. With atoms and finding out the how many atoms are in each thing, or how many atoms there are. Don't overcomplicate it. Stay with grams, stay with mass, and then go to moles. Make sure you separate, and I'm going to show you what I mean. Make sure you separate certain atoms away. So, for example, this one, how many copper atoms, Cu, are in 10 grams in this compound? So one way to do it is to take the 10 grams of this compound that you have, multiply by 1 mole of that compound divided by the entire molar mass of that compound in grams. And then also multiply it by how many moles of copper you have divided by the mole of this. So that will cancel out that. And then you end up with Cu atoms. So if Cu was 2, like Cu2 then continues on with the compound, then it would be 2 moles of Cu for 1 mole of this compound. Does that make sense? And then multiply it by Avogadro's number times atoms, and that's what you get. So that's probably the easier way to do it. Maybe another way that I was introduced to how to do it is you take the weight of copper and the weight of the total compound. You find out how much of that is copper, and it turns out to be 13.43%. And then, so then you could take 13.43% of 10 grams, and it would give you the 1.43 grams of copper. And then you do a normal conversion from there, and then you get the same answer on both. Okay, so that was problem set number 4. Comment any questions.